receiving this signal ym, and we compared it. So this is the processed signal. Oops, sorry. This is the unprocessed. One thing that we noticed yesterday was that the processed version has colored noise. I see. Colored noise. And the unprocessed version has white noise. So we will focus more on the unprocessed version. Furthermore, now on the unprocessed version, right here, on the unprocessed version, consider these simplifications. One, assume the channel to be causal. In that case, these HKs, HK disappears for k less than 0, right? And we get this. And the other simplification that we assume is that suppose we transmit a symbol at time 0. Transmit something time, then its effect in the system can be felt only for a finite this. Let this duration be L. Fine. Simple assumptions.
Yes, sir.
So
Yes, sir.
in this case, the unprocessed received signal takes this form. Fine. Where now I can write HM channel right? Fine.
Yes, sir.
Yes. So
So
now
IM is the transmitted signal or the transmitted symbol?
transmit symbol. Fine. We generally use these interchangeably. Also, you won't. This I'm not following from any book. This part or starting today, I'm not following any book for this course. This is what I know. So I'll provide you
Okay,
the
sir.
notes. I will provide you the handwritten notes once the syllabus is complete or once this part is complete. But I do not know a direct reference. So this equalization part is actually generally given very badly in both the books all the books I know. And it's hard to follow from there. So that's why I'm doing it this way. Fine. So now we we see that the channel behaves like an agreed. The channel behaves like an FIR filter.
Yes, sir.
So equivalently, can define fine.
Yes, sir.
Great. So this also again and our job is to know what are these right. This is our job.
Yes, sir.
So here HNs may or may HNs may or may not be known. Let us first consider the simple case where HN or pulse is known. Fine. Let us first consider that case. So in this case, here, if we start symbol transmission at 0 n equals 0, transmit till then right.
Yes, sir.
right? Fine.
Yes, sir.
I capital N minus K plus 1 minus K. Right? Agreed with the system of
So
equations?
why is there not a
Yeah.
sum term in Hn plus L?
Sorry.
Why is there not a sum term in Rn plus L?
So we stop at the nth instant.
Oh, okay, okay, sir. Okay. And there are I mean, L
Yes.
coefficients of, okay.
Yes. That's why n plus 1 starts from k equals 1. This is k equals 1. This is k equals 0. And for once, this is not an error. Fine.
Okay, sir.
Great. So can now define. I can now define this vector. So let's say define the vector A. So everything else remains the same. R as fine. N plus 1. Fine. I could have as well defined these indices as -1, but that's cumbersome. Fine. I can write these vectors.
Yes, sir.
I can then write fine. I can define this matrix like this.
Yes, sir.
So simply I can say R equals plus W and want to find the that this. Okay. So the maximum likelihood solution to this problem is a hat equals r x a in I to the power n, sorry, s to the power n, where s is the generating constellation. Fine. The optimal search that we have talked about earlier.
Yes, sir.
Yeah, but this has high Schnell complexity s to the power n. Complex multiplication. right?
Yes, sir.
So we look for something simpler. And that context instead pose the problem as, let us find the a hat equals, sorry, argmin. This should be min, not max. Min. This, and then fine. Does this make sense? Does this procedure make sense?
Sir, what does round of a hat mean?
Round means that, okay, so let me elaborate this. Minimize instead of minimizing r minus ha over sorry Sn, Sn minimize uh, sorry, I'll work on this later. Minimize it is the screen visible?
Yes, sir, the screen is
Yes,
visible.
yes. Minimize it. The pen has for some reason stopped working. I'll just close all the unnecessary windows. OneNote has crashed. So this, let me write it again. Let me write, instead over Sn, it, minimize it over or c to the power n, and then for each entry of a hat, choose the symbol nearest to a hat from.
Sir, but won't Rn be bigger than Sn?
It is bigger, but we have the luxury of continuity.
Okay, sir.
S to the power n is a discrete set. So we have the combinatorial problem of choosing one out of the n solutions, right? So it will become clear to you.
Yes, sir.
Fine. Or rather, I would say that this, I would give you the example of JE. Suppose you have some question, some crude integration, and you get 4 options. And the 4 options are 3.46, 3.48, minus 3.46, minus 3.48, and your answer is 40 ohms. So that scares you, right? But the problem is that instead of back sub, or actually what you would do in multiple choice questions is that instead of trying to back substitute all the options and then calculate, you would try to calculate the answer and see which one gives you the best fit, right?
Okay, sir.
So that is what we are doing. So this, so for this, we simply say that a hat equals square equals right. This is right.
Yes, sir.
Now what would we do? We have moved from a discrete space to a continuous space. I'll call this J. Right. This is what I will do. I can do this.
Yes, sir.
So differentiating this 0 plus, actually this is a vector. Zero. Right? Or H Hermitian H A fine, I would say H plus H. This beast. Fine.
Yes, sir.
So have you ever come across this term?
Pseudo inverse.
Yes. So others, have you heard of this term?
So it was taught in DSP, sir.
DSP were taught pseudo inverse.
Yes, sir.
Why would he teach pseudo inverse in DSP? I thought this was the from the wireless
This
course
is
I told you.
moving average. He was estimating the moving average one, so he found out the moving average filters. So he was.
Okay, moving average filters you have done. Nice. So this
Can
is
you
the
can you go up a little bit?
yes, Adit.
Okay, sir. Thank you.
This is the Moore-Penrose pseudo inverse. H dagger H dagger H A plus H dagger. Not a plus sign, this is a dagger. This is the dagger actually. So I'm just it becomes slightly different every time. So dagger to dagger. H dagger W. Fine. So this equals H Hermitian H inverse H Hermitian H A plus H dagger W. Fine. So note that this H, because you might ask, or someone might ask that why don't we simply take H inverse? Yeah. Answers?
Sir, it might happen that it is singular. So,
There is a bigger problem than that.
the problem.
Yeah, there's you have a bigger issue than that. Is or is R is n plus 1 times 1. Right? So H is right.
So we can't calculate the inverse of H inverse.
Yes,
I mean H.
only square matrices are invertible. H is a tall matrix and only square matrices are fine. So now, therefore, A plus this. Right? Noise is 0 mean? Fine. Fine.
Yes, sir.
Yes. So, and letting A tilde equals A minus What will I get?
So
Okay, let
power
me do
spectrum,
it. No, the covariance matrix.
the
This
COVID.
is the noise matrix equals right.
Yes, sir.
There should be an expectation here. Expectation goes inside. I so H Hermitian H, right? H Hermitian H, not H Hermitian. Inverse H Hermitian and not outside H. This you can try yourself, and this becomes N naught. This is the noise covariance matrix. Fine.
So N naught is the power noise power spectral density, right?
Yeah, noise variance. Now we'll only talk about variance.
Yes, sir.
We
Sorry.
are everything we are doing is in the discrete domain, or we are totally dealing with discrete. So that's why I don't like the treatment by many of the books, because they still try to follow that power spectral density and all that kind of a notation, whereas we are purely doing digital signal processing here.
Okay, sir. And H, relation H is, I mean, H is the channel coefficients or
Yeah,
the
H is the
input
matrix containing channel coefficients.
coefficients. And this is called the noise covariance matrix, or this is equal,
This
I
is
mean,
the
to
noise
previous.
covariance matrix. The post processed noise variance matrix. Fine. Now see that our job was to extract the vector from our right.
Yes, sir.
So the channel had different response for different Cs or unequal response for Cs. We try to undo that via some right. So this process of reversal the channel called equalization. Fine. We had an unequal channel. We force it to be equal and we call it equalization.
So how
And
can we supposed to be equal?
this particular solution the equalization problem is zero forcing solution. Fine.
Sir,
Yeah.
so could you explain once more how exactly we are equalizing?
Just a
Because
second,
I
Adit.
thought that the
Let
calculation
me
had a.
turn up my speaker volume. Yeah, now you repeat.
Am I audible, sir?
Yes, now you're audible. Speak.
Yes. Uh, what I was saying was that I didn't get how exactly are we equalizing because the channel coefficients have a delay associated to them, so that we are getting some ISI. And
Yes.
is that in some way related to unequal frequency response? And how
Yeah,
are we
so
exactly?
one. So that's why I let's answer your question step by step. So we have HK. Channel can be seen as an so any FIR filter will have a frequency response.
Yes, sir.
And having a frequency response means that it'll behave differently with different frequencies. Adit,
Yes, sir.
answers your question.
Okay, sir. Yeah, that answers my question. And then
Yeah,
how are
next.
we equalizing?
This by forcing by we are effectively removing the effect of channel or we are undoing the effect of the channel by using that pseudo inverse trick.
Okay, sir. So basically, we are, I mean, the decoding process that we have used to figure out the estimate, that
Yes, that is
in
equalization.
itself is the.
Yeah,
Okay.
that is equalization. So if you open that Procase and Salahi textbook, that guy solves the same problem in terms of Z transforms. But
Okay, sir.
the way I understand it, that becomes quite complicated, quite fast, or that escalates quite fast. So this is in terms of things that we have already discussed in detail. So you have had a course on DSP, and you have had courses on linear algebra. So that way, this form of the solution is more tractable
Yes, sir.
or more easily understandable for us, even for me. Another way, so here we are the zero forcing solution. We ignore the added noise and focus only on minimizing the or focus only on oh we ignore the and focus only the diff channel, right? That's what we have done.
Yes, sir.
So that is why this is called zero forcing, that we assume, in other words, we have assumed that the noise has been forced to zero, or this case the noise is forced to, and this is called the zero forcing solution. The other equalizer is that the linear minimum square define a hat equals, say, what symbol should I use? Z we haven't used, right? We haven't used G as well. G Hermitian Y, where G is an unknown vector such that expectation of okay, so let's do this slightly differently. Fine. So I will, like I defined the LMMSE in the zero forcing solution after I had described the procedure. Let us describe the procedure first and then talk about the definition or meaning of the terms, right? So now let yeah, let for some m capital M y equals n plus m minus 1. Then W, and we used R, right? So sorry, scratch that. Let for some m or let's do better. To Rn fine. So it contains the m minus 1 past values and m minus 1 future values. Fine.
So,
And this we have taken this because each received sample contains effect of past samples and is affected by and affects future samples. Or if we are interested in IN and receive Rn, then Rn is affected by past samples, right? Rn is affected by the past samples or past values of in. And in some information about in will contained in the you agree with this statement?
Yes, sir.
Yes. So order to extract in, we need both the past and future values of the past to cancel the effect of others and the future to extract all the information, right? Make sense, guys?
Yes,
Yes.
sir. It makes sense.
So let us without the loss of fix Rn. Plus n, right? This beast, and let a hat n. Fine. Fine.
Yes, sir.
Okay. Great. Now,
So G is the channel coefficient or the signal?
no, G is a linear combining vector that combines different R's to obtain an estimate of find this. Okay. Fine. Guys, Adit?
So,
Yeah, fine.
so we have to estimate GH.
We'll come to that.
Okay, okay, sir.
That's what we are solving for. Now we choose this G and the mean squared error between an and then is that is Gn equals R min to G an single minus equals fine. Oh, sorry, this is a scalar. Fine. Okay.
Yes, sir.
An is same as In. Just that it's harder to use capital letters for some things, so I used An here. This is same as In.
That be GHRN. It is.
Yeah, R, GHR.
Okay, sir.
Fine. So
Yes, that
this
makes
G
sense.
Hermitian. So again, I expand this. See, we know that An is a random sequence, or this In is a random sequence, that we know. So this plus G Hermitian expectation of RR or Rn, actually G Hermitian Rn minus G Hermitian Rn minus An R Hermitian Fine. Fine.
Okay, sir.
Now for the ugly part. Okay, so I won't solve. I'll solve these later because we don't have much time now. Let expectation of Rn Hermitian be sigma R let Rn A conjugating and fine. Both won't be there. Fine. Valid assumptions.
Yes, sir.
Again, so J becomes sigma A square plus G Hermitian sigma R G minus G Hermitian psi RA minus psi RA Hermitian. Fine. Differentiating this with respect to G, I get sigma R G minus psi psi RA or psi R. So sigma R minus sigma inverse. Fine. This is fine, guys.
Yes, sir.
Great. So now let us spend some time in calculating this sigma R and psi R. Minus fine. Expectation of this thing. R L R n minus L summation HK A HK. Right? This is what we have defined earlier.
Yes, sir.
So for simplicity, let A be and this we can assume for simplicity. Otherwise, life will become too complicated. It's already quite complicated. We don't want to complicate it further. So in that case, R minus L n minus m expectation equals actually L equal to 1 to capital L, K equal to 1 to capital. Sorry, this should be K. This should be K. P equal to 1 to capital L, K equal to 1 to capital L. Sorry, 0. HK, one of these should be P. Okay. So the laptop has maxed out. Uh, I'll see if I can continue this on Tuesday. Fine.
Okay, sir.
Okay, so what I will do is I'll finish. So the topics that we'll cover is this equalization and 2 lectures on OFDM. So we have stuff for 3 to 4 more lectures on in this semester, and then we'll be done. Fine.
Okay, sir.
Okay. So no need to watch either wireless or synchronization.
Okay, sir.
I'll teach whenever I can.
Okay.
Okay. Bye then. Have a
Thank
nice
you,
day, all
sir.
of you.